Example, a rotor with a 44-inch diameter fan weighs 1,000 pounds and turns at 2,220 RPM. The rated bearing capacity is 20,000 pounds. The calculated bearing life is about 60,000 hours. If the fan has 1 ounce of unbalance out on the edge of the fan, it will have 22 ounce-inches of unbalance. We can calculate the additional load of this 1 ounce of unbalance due to centrifugal force. The equation can be simplified to the constant 0.00639 times the unbalance in ounce-inches times the square of the speed in hertz. Plugging in our numbers, 22 ounce-inches of unbalance times 37 hertz squared gives us the result of 192 pounds. This means that, due to centrifugal force, a 1 ounce weight, 22 inches from the center of this rotor, adds an effective weight of 192 pounds to the rotor. This is nearly 20% of the actual rotor weight. In the bearing life formula, when we add this weight to the rotor weight and run the equation again, the result is about 35,000 hours. The life loss due to the 1 ounce of unbalance is 25,000 hours, which is 42% of the original life. From this example, we see how unbalance affects bearing life. The levels of vibration affect bearing life in much the same way. Assuming an overall level of 0.2 inches per second is normal vibration yielding a 100% bearing life, then increasing the overall vibration to 0.6 inches per second yields only 31% or less than 1/3 of the normal bearing life. To extend bearing life, it is imperative to pay attention to the peaks in the lower frequency range of the spectrum, which are commonly the root cause of the bearing degradation, such as misalignment or unbalance. Remember that our earlier discussion on viewing data pointed out the benefits of displaying spectral data in velocity, with the specific goal of seeing these low-frequency peaks as well as high frequencies. This spectrum has peaks that are indicative of bearing problems. Let's look at the setup required to collect data that ideally maximizes your ability to capture bearing degradation. The maximum frequency should be set depending on the bearing and the speed which it is turning. Race defects will show up in the higher frequencies first and could be as high as the number of rolling elements times the calculated race defect frequency. This small bearing has 8 balls and has an inner race frequency of about 5 orders of turning speed. This means that defects could reasonably appear as high as 40 times turning speed. This bearing, on the other hand, has 19 rollers in it. The calculated inner race frequency is about 11 orders of turning speed. 19 rollers times the inner race frequency is 209 times turning speed. Again, realize that these are idealized for the bearings only. No other considerations have been made. Practically speaking, both of these would probably be modified. If the small bearing were in a motor, then rotor bar problems would be missed if the maximum frequency were only to 40 orders. If the large bearing is turning very slowly, we may be interested in multiples of gear mesh that may be outside this range. When shaft speeds are above 15 hertz, defects can be found when the resolution is only 3 to 5 hertz per line. For bearing speeds below 15 hertz, the resolution should be 1.5 to 3 hertz per line. A general purpose maximum frequency, that is a good compromise for garden variety equipment without gears such as pumps, motors, fans, etc., is 65 times the turning speed with 800 lines of resolution. The spectrum can be divided into 6 separate bands or parameters. These bands can each have its unique alarm levels. For these rolling element bearings, CSI recommends 5 spectral bands plus 1 variable high-frequency band. The first spectral band should include the subharmonics and the 1 times energy. Typically, set the cutoff at 1.5 orders. The second spectral band includes the energy at 2 orders, so its upper limit is 2.5 orders. A band set from 2.5 to 8.5 orders covers looseness and vane pass. The next 2 bands are bearing bands. The first bearing band spans from 8.5 to 35.5 orders. The second bearing band spans from 35.5 to 65 orders. The sixth band, as mentioned earlier, is used for the variable high-frequency band from 1 to 20 kilohertz. This last band is in acceleration and is outside the parameters of the stored spectral data and is only a trended value. Again, realize that these recommendations are for normal garden variety pumps, motors, fans, and so on. Special applications such as high turning speeds, above 100 hertz, or extremely slow turning speeds may require special settings. Explanation of these bands and recommended alarm levels for each band are covered in the program Rolling Element Bearings, Severity Determination. While many areas have been covered, we've only highlighted the most common problems and characteristics. We realize that unique design and applications may cause you to see other characteristics in spectral and waveform data. Thank you for joining the thousands who have recognized CSI training as leading industry with quality information, instruction, and application of PDM and RBM techniques. We are confident that the application of these tips and techniques will help you succeed in your analysis of rolling element bearings. We look forward to assisting you achieve success in your future endeavors.
CSI, changing the way the world performs maintenance.